Hi, I'm Justin Johnson, and today I want to talk about work that's been going on in my group at the University of Michigan on learning visual representations from language. This work was mainly led by my PhD student KD, but for the second project, Gaurav and Zubin also helped out. So before we get to that, I want to talk a little bit about how we typically pre-train in vision and language tasks. Well, usually we actually treat vision and language tasks as being downstream from vision tasks. And what do I mean by that? It means that first we start by learning good visual features via something like ImageNet classification. And then only after we've learned good generic visual features, we transfer those features to some downstream vision and language task like image captioning. So this puts vision actually first, and then we always do vision and language second. And this actually has gotten more complicated in the last couple of years as people have started using these large multimodal transformer models for vision and language tasks. And of course, their pre-training scheme is actually even more complicated. So a pretty typical pre-training scheme is to first start by training some visual backbone for classification, usually on ImageNet, then adapt that visual backbone to perform object detection, and then set aside those visual representations and go and pre-train something like a BERT model on a whole bunch of textual data, and then combine together this textual encoder and this visual encoder into some big joint multimodal transformer, and then finally fine-tune it for the ultimate end task of vision and language. And now this pipeline has become pretty standard, but I think it's actually problematic. And it means the performance on our downstream vision and language tasks is bottlenecked by this unimodal pre-training. This is actually even worse because in many cases the visual backbone is not even fine-tuned in these approaches. So our philosophy is a little bit different. I think that vision and actually language should be downstream from vision and language. What do I mean by that? I mean that I think the way we pre-train our representations in general should not be unimodal, but multimodal. We should learn visual features directly using language annotations on some joint multimodal vision plus language task. And in the process of learning features for this multimodal task, we'll end up learning powerful visual features that can then be transferred to downstream visual tasks. I actually think that vision and language, rather than being an application, should be the core way that we learn our visual representations in general, for any kind of vision tasks. Why should we put vision and language first? Well, for one reason is this idea of semantic density. If we're going to learn visual features, we need to learn them from some kind of pretext task or some kind of pre-training annotations. So we can think about what types of tasks can we consider using and how might they compare with each other. So for something like contrastive learning that's often used in unsupervised learning, there's no semantics in the pre-training task at all. Something like image classification gets a little bit of semantics because we're asking the model to predict an image label. Something like multi-label classification or object detection involves a little bit more semantic density, that is like more semantic knowledge required per training instance, because now we're asking a model to predict multiple objects or semantic labels from an image. But something like captioning, where we're asking a model to predict a piece of text from an image, has extreme semantic density. In order to predict a caption, like an orange and white cat near a plate on a white cake, the model needs to recognize multiple objects, their spatial relationships, attributes of those objects, as well as perhaps any activities or actions they're participating in. So this means that one training instance where we predict a caption requires the model to recognize a whole bunch of interesting, useful semantic stuff in the image. So for this reason, I think that vision and language tasks should make a very good learning signal for learning powerful visual representations efficiently. A second reason why we might want to put vision and language first is the ease of data acquisition. So first, even if we're in the regime of supervised annotation, where we're paying human annotators to collect data, then I think that asking annotators to write captions is much more natural than asking them to verify image labels in a big semantic label hierarchy. And this also leads to a much more simplified data collection pipeline. We don't need to generate a semantic hierarchy and do instance spotting and all these other tasks that are necessary for something like object detection annotations. And the other reason is that vision and language data naturally scales up to web scale data. There's tons of images out there on the internet, and they don't occur in isolation. Whenever there's an image on the web, there's almost always going to be some kind of language nearby, and we should be able to make use of that language in our pre-training pipelines. So with this philosophy of trying to put vision and language joint training first as the primary way to learn representations, we have a paper at the CVPR called Vertex, Learning Visual Representations from Textual Annotations, that shows how we can make this work. And the pipeline is actually fairly simple. We are going to jointly train a CNN and a transformer from scratch to do captioning on Coco using a fairly simple architecture, right? We just pass our image in through a standard ResNet 50 backbone, use a linear projection layer to project the ResNet features, then pass those projected features into a textual head, which is a bidirectional autoregressive transformer with one forward transformer predicting caption tokens one at a time going forward, and a backward head predicting caption tokens going one at a time backward. And these transformers are just super standard multi-headed attention transformers that everyone uses these days. We train this entire model jointly end-to-end to perform image captioning on Coco, and then we take the visual backbone, the ResNet 50, and then transfer it to many, many different downstream visual recognition tasks. Now, our key result is that when we learn visual representations via language in this way, we end up with very data-efficient learning. One of the downstream tasks we look at is linear classification on the Pascal VOC classification dataset. So here we plot on the x-axis how many images do we use for pre-training. And then the y-axis shows us what is our mean average precision on Pascal VOC once we train linear classifiers on these learned representations. And we can see that the green curve here gives us the performance of standard fully supervised pre-training on ImageNet. We also compare here with Perl and Moco, which are two self-supervised methods that don't use any labels at all, and they're a bit worse than this fully supervised approach. And now our approach, Vertex, which trains on using Coco captions, is able to learn really powerful representations using quite a lot fewer images than ImageNet pre-training. So here the blue curve is showing if we train Vertex using all 5 captions per image in Coco, and the orange curve shows us what happens if we use only one of the 5 captions per image in Coco. And now a couple observations here is that for the same number of training images, using captions gives much better visual representations compared to using ImageNet classification labels. This means that our language supervised training approach is extremely data efficient. A second thing to note is that when we use all 118 Coco images, then we're able to learn visual representations that actually slightly outperform supervised ImageNet pre-training that uses 10x more data. So again, that shows the utility of this idea of putting vision and language training ahead of vision tasks. In addition to VOC, we look at some other tasks, including ImageNet linear classification. And I should note that this one is really unfair to our model, right? Because in this case, if we're comparing with supervised ImageNet pre-training, then the pre-training task and the downstream task are actually the same task. So supervised ImageNet pre-training has a massive advantage here. But even so, our model is able to perform pretty much on par with supervised ImageNet pre-training. And we compared a bunch of other tasks in the paper, but the main takeaway here is that this approach of using image captioning as our pretext task, it learns representations that are as good or better than those learned on ImageNet in many cases. Given the success of this approach, the next thing we wanted to do was try to scale this up. But as we were thinking about scaling this up, OpenAI and Google came out with some two interesting papers that did something very similar. They had these two projects, Clip from OpenAI and Align from Google, that use this very similar approach that we pioneered in Vertex of using vision and language pre-training to learn good visual features. Their approach is a little bit different. Rather than performing image captioning, they use contrastive learning. So they pass an image through a visual encoder and a piece of text through a big transformer-based textual encoder, and they train with a contrastive learning objective to say whether or not the image matches the piece of text. And by training this on a bunch of data, they're able to learn really powerful visual representations that transfer to other downstream tasks. So to me, it was pretty validating to see that this idea of learning visual representations from vision and language actually works really, really well and can indeed be scaled up to these very large web scale datasets. The issue with these approaches is that they train on these gargantuan datasets that are extremely noisy, non-public, and not really accessible to anyone else in the community. So Clip trains on about 400 million image text pairs, Align trains on about 1 billion image text pairs, but both of these are private internal datasets, and they offer really very little information on exactly what's in those datasets, how they were collected, or what they could be used for. So we set out to think about what are the different types of image and text datasets that are out there, and could we use them for further exploring this idea of learning visual representations from language. So on the left-hand side here, we have these sort of medium-scale datasets like Flickr30K and Coco captions that consist of images and captions that were manually annotated by human annotators paid on crowdsourcing platforms. These are valiant efforts and they have really high quality data, but it's really expensive to scale these types of annotations up. So on the right-hand side here, we've got these gargantuan entire internet data sets used by Clip and Align that basically scrape the entire internet. They perform very little filtering on the data that they get. And actually, we don't really know what's in there because the papers offer not much information on what data is there, and it's non-public, so it can't be used by anyone else. Now, in the middle here, we've got these large-scale data sets, maybe in the millions to tens of millions of instances, that scrape or search the internet to get images and corresponding text, but use fairly complicated automatic filtering in order to get that data. So in this category, we have the fairly pioneering SBU captions dataset that has about 1 million images from Flickr. But the ones that are more commonly used these days is this conceptual captions dataset. There's a 3 million image version and a 12 million image version. And the 12 million image version is actually brand new and also being presented at this CVPR. So because conceptual captions is, I think, the most commonly used publicly accessible vision text dataset, we wanted to dig in and see how is that collected and what are the properties of this dataset. So conceptual captions, their basic idea is to collect images and text using the alt text attribute in images. You know, when you put an image up on the web, you can attach an alt text attribute to the image so that in case the image doesn't load or in case a person is visually impaired, then there's some text fallback to show the content of the image in either of these cases where a person might not be able to look at the image. This image alt text strategy is very clever, but image alt text tends to be extremely noisy. So to get any useful data out of image alt text, conceptual captions has to use this extremely complicated heavyweight filtering and pre-processing pipeline. They use part-of-speech tagging and sentiment analysis on the language and use a bunch of heuristics to kind of try and throw away pieces of text that are not interesting. And they also summarize and rephrase the text using, again, NLP techniques to kind of throw away proper nouns and dates and things like that and clean it up and make it more generic. And now the other part I find kind of troubling in this data filtering process is that they actually use Google Cloud Vision APIs to recognize what is the visual content in the images, and then throw away any instances where the recognized visual content does not match the nouns that are found in the text. I think this idea is very clever, but there's some problems that come out of this pre-processing pipeline. One is just the very nature of the data is that the text is somewhat secondary to the images. Not that many images on the internet have really high quality alt text. And indeed, people are only looking at alt text in a fairly small fraction of cases. And as a result, alt text is often overlooked when people are putting images up on the web. Another kind of subtle problem is actually the use of these visual classifiers in the preparation of the conceptual captions dataset. It makes me kind of uneasy that the preparation of the dataset relies really deeply on these visual classifiers. Suppose there's some visual concept that we'd like our dataset to contain so that we can learn to recognize it, but it's not currently recognized well by existing classifiers. Well, then such an image is not going to end up appearing in conceptual captions because the Google Cloud Vision APIs are likely to fail on that instance anyway. So there's potential for subtle bias in the type of content that shows up in conceptual captions due to its underlying reliance on visual classifiers in the dataset preparation. Another issue with conceptual captions is that this filtering pipeline has extremely low recall. In the conceptual captions 3M dataset, they start from a set of 5 billion initial images, and through all this filtering and preprocessing, they only end up with about 3 million final images. This low recall of their filtering procedure means that it's actually fairly difficult to scale up this kind of pipeline, even for folks at Google. So at this CVPR, released a new version of conceptual captions that pushes it up to 12M, using a fairly similar data collection pipeline. But the main way that they scale up is actually like they've already scraped all the images they can find. So the main thing that they do is relax some of the filtering constraints in their preprocessing pipeline. And they admit that this adds a lot more noise to the captions in conceptual captions 12M. And here on the right are a couple examples from their figure 1 of their paper to just show that a lot of the text appearing in conceptual captions 12M could be very noisy and really might not be natural language at all. So then after we looked at all these alternatives, we weren't super happy with any of them for the reasons we discussed. So we were left with this question: if we want to continue pushing this direction of learning visual representations from language, then what's a good source of data? Is there some way that we can get large-scale, high-quality data without complex filtering that relies on these use of visual classifiers under the hood? Our solution here was to build a new vision and language dataset that we're unveiling here for the first time, called RedCaps, which consists of images and captions from Reddit. Reddit is a social media website that probably many of you are familiar with. It's one of the top 10 traffic websites out there on the internet, and it actually has a lot of appealing properties for collecting really high-quality vision and language data. A lot of posts on Reddit actually share images along with text describing those images. Unlike alt text in conceptual captions, this puts the image and the text on the same footing for the original purpose of the data. The captions were written by people to be shared explicitly with other people. Reddit also provides a fairly convenient official API for collecting data, so we do not have to resort to web scraping. Another really useful property of Reddit is that it has an extremely active community and moderation team, which means that low-quality content gets either downvoted by the community or removed by moderators. Reddit consists of independent subreddits, and these subreddits are their own independent communities with their own rules and culture. And this use of subreddits is really interesting because each subreddit has its own rules that dictate the type of content that can be posted on those Reddits. And some of the larger subreddits have extremely stringent rules. So here are the example rules from the I Took a Picture subreddit, which is a subreddit for photography. The one that we found most interesting was this rule number 5. All submission titles must start with ITAP and only describe the contents of the image. Keep titles short and concise and compose a literal, objective description of the subject. Do not include your intention, reaction, interpretation, backstory, process, equipment, social media info, clickbait, memes, emojis, don't write in all caps, etc., etc. So basically, this is the perfect type of data for vision and language, right? They're interesting images, they're interesting high-quality text that objectively describes the content of the image. This is exactly the type of data that we want for learning good representations. And now another interesting thing is that there's so many different subreddits, and each subreddit caters to a different audience. As a result, the images and especially the descriptions of the content in various subreddits is often catered to experts and therefore fairly detailed and fine-grained. And now this use of subreddits gives us a really interesting way to construct dataset. Rather than going on the one extreme of COCO and manually annotating every instance, or going on the other extreme and scraping data arbitrarily from the web and then trying to filter it, instead, our strategy is to curate at the subreddit level. So we go in and find subreddits that have really active communities that are producing interesting high-quality data, and only collect images and captions from a manually curated set of subreddits. And by curating data in this way, it lets us steer the overall composition and type of data in the dataset without resorting to annotating individual instances. As a sample of the types of subreddits that we collect data from, we take data from subreddits about general photography, like I Took a Picture, or RPics. These can really have pictures of anything, but they tend to be fairly high quality with very descriptive captions. We have subreddits about animals. These are often geared towards enthusiasts. So for example, in the RBirdPics subreddit, they often mention the species name as well as where the photo was taken. There's also subreddits about fairly obscure animals like axolotls. Another really interesting note here is that even in cases where the caption itself might not be super informative, like Sir Fluffy Gills or Best Friends, the subreddit name itself provides some really powerful supervision for the visual content in these images. So that's another really useful property of using subreddits. There's subreddits about plants. So these, again, are geared towards enthusiasts, often mention the really fine-grained details of exactly what species, or flowers, which again mention individual species of flowers. There's subreddits about food, maybe about particular types of food like sushi or healthy food. These will go in and describe all the types of things that appear, like chicken breast salad with the ingredients of onions, strawberries, avo, nuts, and lime. There's subreddits about objects, like artifact porn. Here, I need to make a digression and just note that just because the word porn appears in a subreddit does not necessarily mean it's pornographic. There's been in-joke among subreddit names that they're often titled with the word porn to indicate non-pornographic beautiful imagery. We don't collect from any pornographic subreddits, but many of the subreddits do include that word porn in the title just to indicate jokingly that they have beautiful images. So there's subreddits like artifact porn that describe ancient artifacts from different civilizations, or motorcycle porn, which again is geared towards motorcycle enthusiasts and describe the fine-grained make and model of various motorcycles. There's subreddits about scenery. Some are generic scenery like mountains, which may also include mountains on other planets, or fairly fine-grained types of scenery like infrastructure porn, people who are really interested in man-made infrastructure in cities. There's also subreddits catering towards particular hobbies, like woodworking or crochet, where people are asking for advice or sharing examples of projects that they've completed. So in general, overall, RedCaps is a dataset of images and captions from Reddit. We manually select 256 subreddits to collect data from, and in total, we collect 11.7 million image caption pairs. And we hope that this will be a really exciting new dataset to help push forward vision and language. There's a bunch of design considerations that we kept in mind when building RedCaps. We use this idea of subreddit curation to manually choose subreddits in order to determine what type of data will be in the dataset. We wanted to choose subreddits that cover a variety of interesting visual concepts, that don't have any non-safe for work imagery. We don't want any banned or quarantined subreddits that might contain fake news or toxic language. We also want subreddits that are primarily based around sharing and describing images. But we wanted these images to be photographs, not memes or drawings or computer-generated imagery. We also wanted to select subreddits where the post titles tend to be descriptive, rather than making jokes or memes or political commentary or something similar. We also made the explicit design goal that we wanted to minimize the number of people that appear in images in RedCaps to try and minimize privacy concerns. So we explicitly exclude subreddits that are specifically built for sharing or describing or commenting on pictures of people, like sharing celebrity pictures or sharing or commenting on selfies. Those we exclude from the dataset entirely. We do a little bit of lightweight automated filtering. We run an off-the-shelf not safe for work detector to try to remove any not safe for work images that might have slipped through the cracks. We also use a block list to get rid of bad words and captions. And we run an off-the-shelf face detector to remove images containing children and to blur the faces of other people appearing in images. But these automated filtering steps are extremely lightweight compared to those used in something like conceptual captions, and they only end up removing about 0.1% of the dataset overall. That means we end up with like 99.9% recall, and that just means that the community of Reddit itself, at least within these chosen subreddits, ends up doing a great job at self-moderating and keeping their content high quality. We expect RedCaps to grow over time. Reddit is one of the most popular Reddit websites on the internet, and its usage has been exploding in recent years. In this initial version of RedCaps, we collected data up through the end of 2020, but looking at the increasing volume of posts on Reddit over time, we can see that future versions of the dataset should be even bigger. We also see that RedCaps has a lot of diverse language. We did some analysis on the number of unique nouns, proper nouns, verbs, and adjectives compared to other vision language datasets, and RedCaps has much more diverse language than these existing datasets. We wanted to show that RedCaps is useful for representation learning, for learning visual features from language. So we, of course, train Vertex models on different datasets, and then compare how well Vertex is able to learn good visual representations on existing datasets, SBU and GCC, versus RedCaps. And we compare both the full 11.7 million version of RedCaps, along with a smaller subset of RedCaps that's more comparable in size to GCC. And now another detail here is that when training Vertex models on RedCaps, we include the subreddit name as part of the caption to be predicted, because as we saw with some of the examples, the subreddit name itself often contains useful supervisory signal for the images. The pipeline is largely similar to that we already saw on Coco. We train these models and then transfer to downstream visual recognition tasks. One of our main results here is low shot learning. So we learn these visual representations on these datasets, and then train linear classifiers in a low shot regime using just 1,000 training examples for each of these 6 different datasets. And we see that overall, models trained on RedCaps do better than other datasets on 5 out of 6. We lose a little bit on Sun 397, but we are quite a bit better on all the other datasets. But now another really interesting thing we can do with the language aspect of these models is that, similar to CLIP, we can do zero-shot transfer that uses no training data whatsoever for these downstream tasks. Rather than training linear classifiers, we write different prompts, one prompt per category in the downstream task, like this is a photo of whatever, and then rank these captions by their predicted log probabilities in the trained model, which then gives a ranking of the categories. And this allows us to do zero-shot classification on these different downstream datasets without using any task-specific training data whatsoever. And here we see that RedCaps does quite a lot better than the other datasets at learning representations that allow for zero-shot transfer to downstream tasks. In addition to using RedCaps for learning visual representations, we think that RedCaps is also a really interesting dataset for doing image captioning. We took captioning models trained on CC3M and trained on RedCaps, and then did a human evaluation to see what types of predicted captions would be preferred by workers on Mechanical Turk. And we found that in general, RedCaps models produce language that is more personal, that is more specific and concrete, more conversational, which was preferred by human annotators to the GCC predictions about 2/3 of the time. Another really cool thing we can do with RedCaps models is controllable captioning. So we can actually control the style of the generated captions. That is, we can give the model an image and say, generate a caption in the style of different subreddits. So for example, for this input image on the left, if we generate a caption in the style of the I took a picture subreddit, then it says, I took a picture of my daughter's blanket. If we generate a caption in the style of the something I made subreddit, then it says, I made a blanket for my daughter. If we generate a caption in the style of thrift store finds, then instead it says, found this beauty at Goodwill for $2.99. On the right-hand side here, sometimes if you feed it images that have nothing to do with the subreddit, then it kind of ignores the subreddit prompt and just gives you a fairly generic caption anyway. So if we give it this picture of Saturn and ask it to generate a caption in the style of our food, then it kind of just ignores the our food style and instead just says that this is the clearest image of Saturn. I hope I've convinced you that this idea of learning visual representations directly from vision and language is a good idea and that we should all be doing it. And now to recap what we talked about Vertex, which is our paper at this CVPR that is able to learn really good transferable visual representations from vision and language data. And then we talked about our new dataset, RedCaps, that scales up vision and language pre-training and is a new dataset of about 12 million images, and high-quality images and captions that we hope will be really exciting new dataset for vision and language research. So RedCaps is coming soon, so stay tuned, and hopefully you'll be able to use it very soon for your own projects. So thanks for listening, and I'll be happy to take any questions offline.